Okay. Go home and watch if you haven't watched Fight Club already. Brad Pitt in there. Or maybe try. Yeah. Okay. Attitude toward Brad Pitt. So yeah, attitude toward Brad Pitt measured by legal. Let's talk about legal fight. Okay. And a lot of questions, more than 3 or more. And of course, the value we have for y here is the average of the group of questions. And let's say that we already test with alpha and then factor analysis already. Okay. So now, let's talk about the relationship between the age and the attitude toward Brad Pitt. Now go back to high school mathematics. We say between x and y, we will have a table of relationship. X here only 3 categories, so 1, 2, and 3. Y here, when x is 1, y is young people tend to love Brad Pitt more than old people. Is that right? So let's say that for young people, we get the value attitude toward Brad Pitt is 5. And then when they get into middle age, it's only 4. Okay? And then the older they get, the more they dislike Brad Pitt. So it's only 3. Okay? So here, if we draw the chart, we have x here and y here. X is 1, 2, and 3. 1, 2, 3. And y here is 5, 4, and 3 here. When x is 1, y is 5. X is 2, y is 4. X is 3, y is 2. So we can easily draw this. Now, tell me, do we really have the relationship between x and y or no? Do we have relationship between x and y?
Yes.
Yes, clearly we have. How about this? What if people in the middle age still have the attitude toward Brad Pitt at 5? Do we have relationship in this case? X is 1, y is 5. X 2, y is still 5. And x is 3, y is 3. Do we still have relationship in this case? Do we?
No.
Relationship or not relationship?
No relationship.
Relationship or not?
Yes.
Yes or no?
Yes.
Still we have relationship. Remember people, relationship. A lot of cases that we have relationship. This one x and y have relationship. Okay. This one they have relationship. Okay. This one they still have relationship. How about this? Still they have relationship. See, a lot of kinds of relationship between x and y. There are only 2 cases that they don't have relationship. What are they? Only 2 cases. First case that they don't have relationship. X changes, but y stays the same. Okay. Whatever the x, y never changes. Okay. So no relationship. Okay. That's one case. The other case is this way. Whatever the y, x never changes. So this is another case that we don't have relationship. Only 2 cases that we don't have relationship. We do not talk about the vertical case. We talk about the horizontal case. Okay. If this happens, means that all the y are the same. Okay. Then we don't have relationship. If only one y is not the same with the others, we will have relationship. Okay. So the text here is about comparing the y when x changes. Okay. Say, how many comparisons we must have? If we have two categories of x, if we have like this, how many comparisons? How many? One comparison, right? Compare between this and this, and it's okay. Here is this way. How many comparisons we have? 3, because 1 with 2, 1 with 3, and 2 with 3. Okay. What if it's 4 of them? How many comparisons? 6 of them, right? So what if there is 10 of them? 10 of x. How many comparisons we must have? Now easy people, it's like this. Let's say k is the number of x, then k multiplied by k minus 1 and divide by 2. This is also high school mathematics. So if we have 10 categories of x, then there are 45 comparisons. And if we have 20 categories of x, then 190 comparisons must be made. So that's why it's very complicated. Okay. Now let's not talk about high school mathematics anymore. We go into what we study in university. It's called statistics. And talking about statistics means that you collect the data from a big range of people, young age, middle age, and old age. For young age, a lot of people, they will give you a lot of values, right? It's not only 5 anymore. Some people will give you 4.5, some people give you 4.1, some people give you 3.7, 2.2, or only 1. Lots of people in young age. In middle age people, still the same happen. 4.8, 3.6, 2.3, 1.4, and more. And in the old people, the same happen. 2.6, 3.1, 1.7, 1.2, 4.1, and more of them. What should we do? If we have only one value like high school mathematics, then it's easy we compare between them. Now we have a lot of values for only one x, a lot of y. What should we do here?
We take the average.
We take the average of them, right? So let's say we take the means and then we compare together. Take the means, easy. Compare the means together. So a lot of works to do because maybe we have 20 categories of x. So 20 means to take and then compare together. Oh my God, a lot of things to do. So how to reduce the things to do, right? Yeah. Good. That's why, yeah. Let's say statistics people think about, what if we talk about another way of thinking? Yeah. And because we compare the means, told you already, there is only one means different, then we have relationship, right? Only one means different, so we have relationship. So the x0 here is always me1, all the means must be the same. That's the x0. Then what is the x1 here? Yeah, at least one mean is different. Okay. If S0 happen, all the means are the same together, then do we have relationship between X and Y? If all the means are equal, then we don't have relationship. So if at least one of the mean is different, then we have relationship between them, okay, between X and Y. But thinking about comparing a lot of means, it is just like too heavy work. So they think about another way to solve this. And who are they? We are talking about statisticians, okay? They are scientists, right? They are scientists, so they are very brilliant. Remember that? Yeah. They are not like us, not like you, not like me. They are scientists. They are brilliant. So they think about another way of thinking. We are always talk about the comparing means, and then we talk about the relationship. But for them, they think differently. They do not like this. They will talk about the relationship first, and then from that, they will talk about the means. If X and Y have relationship with each other, then at least one means is different. Okay. If they don't have relationship to each other, then all the means are the same. That's what scientists think. Okay? And that's what they do. And we will try to think like them. So that's why they do not talk about the means first. That's how we do. They think differently. They think about the variance. And what is variance? Variance means that the difference between numbers. Okay? They think about the difference between numbers. Now, say, the values of young people and the values of middle-aged people are different. Okay, they vary. They are different. Between the group of young people and the group of middle-aged people, they are different. What caused that difference? Between the group of young people and the group of middle-aged people. Different, right? But what caused it to be different? What caused it to be different? Between two groups, young people, middle-aged people. What caused that? What happened to you? Variance doesn't mean vary. And I'm talking about, they are varied. You say, they vary because they vary. Between two groups, young people and middle-aged people, they are different. What caused them to be different? Yeah? No, that's wrong. Between you and me, we are different. What caused us to be different? Yeah, even not with experience, I'm still different from you. Let's say I'm still an undergraduate student, just like you. But I'm still different from you. What caused us to be different? Very easy, people. Between young people and middle-aged people, they are different because of their age. Because of their age. So that's why scientists said that, between young people and middle-aged people, they are different because their age caused that. Now, say, talking about the variance, they use SS sum of square to talk about that. Okay, and you studied that already in SMA, I suppose. Yeah. So we have sum of square between groups. This one is caused by the age is caused by the X, or we call the IV. Okay, age, or we say that's the IV. However, you can see here that not only between the groups, but inside the group, only young people, they still don't have the same value for the attitude toward rapid. Okay, only inside the young people. For example, you will answer the attitude toward rapid as maybe 4.5. That guy may be 5. You may be only 3.7. Okay, different. Only young people. What causes that? Still inside the group, they vary. Okay, what causes that? Young people should have only one value for something, right? But no. Yeah, what? What? Yeah, maybe education. The more you study, the more you like or you don't like rapid. Like or don't like?
It depends.
Don't like. Yeah. Why? A lot of things may happen, may affect that. Okay. Example, the first is gender. Male and female who love Brad Pitt more. Male and female who love Brad Pitt more. Female. Why? Because Brad Pitt is handsome, and we male, we cannot feel that, right? Yeah, we cannot feel that very good, but female, they can feel that. Yeah. Okay, gender is one thing. What about other things? Education, just like you mentioned. Okay, what else?
Hobbies.
Yeah, hobbies. Hobbies. Example, you have the hobby of what? Reading books more than playing sport. Then you don't like Brad Pitt as a guy who play gym. Okay, so you see. They say that the SS within group. Within the group means that inside of one group we still have variance called SS. You know that already. Sum of square. Okay. This one affected by other things. Other things that are not in our model. The model here is only age affect attitude toward rapid, but other things happen. Other things affect the attitude toward rapid. So the within group here, SS here, SS within group, is not because of the age anymore. It's because of the other things. So they call it error, or they call it residual. Okay. For me, I love the name error. Error because it's not in your model. Remember, model here only 2 variables, and those are the things outside of our model. So error. Okay. And we want our error to be big or to be small. Big or small? Should be smaller, right? Should be smaller. Then how can we reduce the error? That's right. We will add more variables into our model. See? We will add more variables into our model. And that's called control variables. Okay? Control. So we say control more variables. And control, what is control? Control is very easy. You put more variables into your model. It's called control variable. Okay? Can you control all of the error? Can you?
No.
No, never. Because there are million things that affect your attitude toward rapid. Okay. Outside of gender, outside of education, outside of our hobbies, you have a lot of things in your background that affect your attitude toward rugby. Okay, a lot of things. Your preferences in celebrity also, and maybe your relationship with his wife will affect how you think about him. Okay, because he just got divorced with his wife, right? Yeah. Okay, so you see, a lot of things in the area you cannot control all of them. And the more you control, means that the more you put into your model, the more you must measure. Okay. Example, now you want to control the gender, then you put gender into your model, then you must ask about the gender in your questionnaire. Is that right? If you want to control education, you put education into your model, then you must ask about education in your questionnaire. See? So, the more you want to control, the more you need to measure, the more you need to ask the population, and the more you need to ask means that the more you spend your money. Because your questionnaire will be very long. And how to make them answer your long questionnaire? How to make them? The only way is incentives. Give them gift. Okay, give them money, and they will answer for you. And it means that it's more costly for your research. So you see, we cannot do that. So you must balance between what you want to control and the money you have. Okay, always that way. Maybe after you do the research, no more money for you in salary. Okay. So now I will run the ANOVA for you to see. But the thing here is, the very big thing here. Don't forget the variance between the group is caused by the age, so we care about this. We care about this. Okay. But how big it is? So we can say that the age really affect the attitude toward rugby or nothing lies in the stick. Okay. The sum of square between groups here, significant or not significant. So it's all about the stick. Now, this one is my model. I have lecturers such a complexity. Choose one, and I will test the relationship between them and between that one and the satisfaction, student satisfaction. Choose one. Yeah. Career development affect student satisfaction. Now my model is career development affecting satisfaction. Okay, that's my model now, and I will test with ANOVA. So look and see. Career development here, cadet. Okay, career development. This one is actually legal. Okay, and it's legal. It means that it's metric. Means that I cannot use ANOVA on it. So what should I do? Transform that first. Make it non-metric. We can make a metric become non-metric. We go transform. We go. And put the guardian here. So the name is CD 3 levels. Okay. Career development 3 levels. Only new value. You know that already. So I make it very fast to the 3, and the new value is 1. 1 here is low perception on career development, low career development, and to the 3 to 3.7, the new value is 2. 2 here means that medium career development, 3.7 through 5. The value here is 3, means that high career development. Continue and okay. Go back here, and we have CD3 levels. Okay. Now career development here is not metric. Let's test. Go. Analyze. And because I told you already, ANOVA is compare means, so you go to compare means. You go one way and another. Okay. The dependent list, dependent variable, put in the satisfaction. And the factor here, put the career development with 3 levels. Okay. Go to post hoc and click LSD because we will need that. And click OK here. Now, look at the result. One way ANOVA only gives you one table. Is the ANOVA. The later thing is called the post hoc test. And we will talk about that later. But here, one way ANOVA. Is that good or not? What about the result here? What do we look at first?
The second.
Always the sig. Okay. The sig here is not sigma. Sig here is significance. Okay. And the sig here is good or not?
Good.
Sig here is good or not?
Good.
The sig here is good. Why is good?
It's less than 5%.
Yeah, less than 5% is good. This one is nearly 0, so less than 5% is good. And what does it mean when it's good? There are relationship between what? Between what? Career development and satisfaction. How many percent that career development affect satisfaction? How many percent? How do we know? Now look at this. The sum of square between groups is caused by the IV. So look at the sum of square between groups here. 108, 6, 9, 2. That one is the variance of satisfaction affected by career development. And the total here, 717,425. This one is the variance of satisfaction in total. So how many percent that career development affect the satisfaction is this one, 108 divided by 717 is the percentage of affected by career development. How about the error? How big is the error here? Within groups here, within group. It's talking about the other things affecting satisfaction, you see. So within group is 608. This one is talking about the error. Okay. The error here is big or small? Big, of course. Big, of course. Why is big? Why so big? Yeah, because we the things that happen to affect the satisfaction outside of career development. Okay. So it's big because we learn things there. So yeah. Now go further into the post hoc test. What does the post hoc test tell you? Because we know that they have the relationship, right? We know that they have relationship means that at least one mean is different from the others. But which one? Okay. Or maybe all the 3 means are different from each other. So here, we look here to know that, which mean is really different from the others. Okay. Here, we have career development group 1 compared to group 2. Look at the 6 and you see, are they the same or different? Between the mean 1 and mean 2. Same or different?
Percent.
It's not maybe.
It's the same.
Are they the same?
Yes.
Now, the 6 here is good or not?
Good.
The 6 here is good. The 6 here is good because it's less than 5%. And because it is less than 5%, it means that those two are different or the same.
Thursday. No. Same.
Different or the same? My God.
Simple.
It means that means 1 and means 2. Mean 1 and mean 2. They are different. Now mean 1 and mean 3. They are different too. It means that all the three means are different. So if we draw the chart between x and y, what should it be? This one is career development, this one is satisfaction. Career development only 3 levels, 1, 2, and 3. It should be like this. Up and then up again. Is that okay? Oh, this one is nearly linear. Okay. Okay? Oh, you don't know how can I write that? Yeah. You don't know? Then look at the mean difference here. See. Number 2 here. Yeah. I minus j. So 2 minus 1 is 7.77. See? And 2 minus 3 is minus 7.2. So let's say that the mean 2 here is around the middle between mean 1 and mean 3. Yeah, look at that. And then you can draw. Okay? Okay. Okay. Look at the 6. We can see that all 3 are different. Be careful with that. Okay. Anything you want to ask me about one way and over? You ask me now. If nothing to ask, we go to two way and over. Okay, if nothing to ask, then we go to two way and over. Now two way and over is talking about two IVs, and all of them are non-metric. That affect the 1 dV. So we have career development in our model already, so put one more variable in, and I will test for you. Location environment. So this is my new model now, career development and location. Environment affect the satisfaction of the students. Okay. My model now has 2 IVs and 1 dV. So you can see location environment here. Really, this one is analytical. Okay. So it's metric, so I must transform into non-metric, record into different. And location environment here, the new name is, let's say, location 3 level. Yes. And why 3 levels? Why not 2? Because I'm lazy, because 3 levels are there already. Okay. So I do not need to write anything else, and I click OK and then go here. Career development 3 levels is here, and location 3 levels is here already. Now let's test the two-way ANOVA. Go analyze, and no, it's not in compare means anymore. Compare means only one-way ANOVA. We go to general linear model and univariate. The dependent variable is still satisfaction and fixed factors. They are CD 3 levels and location 3 levels, and click OK. Now, do not care about the first table, okay? It's talking about, only the numbers of respondents in each case. But let's go to this. Now, when you go with the two-way ANOVA, the first thing you must read is talking about the interaction between the two IPs, okay? The interaction between them. So what is the interaction between career development and location environment? What is the interaction? Interaction is this way, people. Interaction is the thing between them that affect the satisfaction. Now, what is the thing between them? It means that, interaction means that if you improve the CD, okay, then the relationship between the location and satisfaction will change. Okay, interaction is like that. So why do we care about this? Because we don't want to talk about that. Okay, I will talk about that later. But the first thing is talking about the interaction between them. Career development and location interacting to each other when affecting satisfaction. And we have the sig of that is 0.544, means that around 54%. Is this good or not?
Good.
Good or not? Good or not good?
Good.
Yeah. The thing here is that when you talk about the interaction between two IVs, you want the sig to be bigger than 5%. Okay. This is the only case that we need the sig to be bigger than 5%. So, yes, because we don't want to talk about that. So, we need the sig to be big. So, the sig here is big and is good. It means that they don't have interacting power when affecting satisfaction. Okay. And it's good. And because they don't have interacting impact on satisfaction, then we can talk about each of them individually. Okay? And when we talk about them individually, then the CD here with the sig of 0, nearly 0, is good or not?
Good.
It's good. It means that the CD here really affect the satisfaction. Okay? How about the location environment with the sig of 46%? Is good or not? No, it's not good. It means that the location environment doesn't affect satisfaction of the student at all. Okay? Okay. Now, we have two more cases to talk about. First case, what if the CD and multiply by log here? What if the interacting power is big? What if the sig of the interacting power is not 0.544 but 0.044? Means that less than 5%. What if that happens? If that happens, it means that if you improve the career development, then the location may affect the satisfaction more, increase the relationship between location and satisfaction. And if you improve the location environment, then the career development will affect the satisfaction more. Okay. So in that case, we cannot talk about them individually anymore because they are, let's say, mixed together. Then when the manager asks you, what should we do in that case? Then we only say that we must improve both of them because they have interacting impact on satisfaction. Okay? Okay? Yeah, that's one thing. What if another case? What if the sig of career development is 0 here, but the sake of location is, let's say, it's not 0.460, but 0.040. It means that both of them are less than 5%, then what should we do? Now, okay, we don't have interacting power, but the sake of both of them are small. What should we do? That's right. We go to the sum of square here to compare between them. Okay? The sum of square here shows that the CD affect the satisfaction more than the location. Okay? 73 and only 1. Now is that good enough for you? Thing here is that I want you to compare between the two tables, the one-way ANOVA and the two-way ANOVA. Now look, the error in one-way ANOVA is 608. Okay, 608. And the error here only 602. What did we say about that? Did we talk about how you control variable, how you reduce the error? See, you want to reduce the error, you put more variables into your model. Here, we put another thing called location environment, and you can see that the error reduced. See? So if you want to reduce even more, we put more variables in. See? Yeah. That's one thing. Secondly, you see the between groups here talking about the impact of career development on satisfaction is 108, but here only 73. What is happening here? Right. Yeah. Right. Where did they go?
CD3 level multiplied by LOC3 level.
Yeah, some of them is shared with the location environment. So yeah, it reduces. Okay, that's about the two-way ANOVA. Remember how to read the table of the two-way ANOVA. Which one first, which one second. Okay. And then what happens if this, if that. Now, let's talk about ANCOVA. ANCOVA is this way, people. ANCOVA. You still want to test some IVs, it's non-metric variables and affecting the DV, one metric variable. But you want to control we have CV, a control variable, and this one is a metric variable. Okay. You know that's something in the error here, in the other things here, affecting the DV, and you want to control it. And I told you already, control means that you put into the model. But this one is metric. So tell me, which one you want to control? Yeah? Facility will be controlled. Now my model is career development, affect satisfaction, location, environment, affect satisfaction. But I want to control the facility. Okay. I want to control the facility. So what should I do? Look at the data. You have facility here. It's already legal. So it's metric. So I do not need to transform it, but I go to analyze, go general linear model, univariate, just like before, and I put the facility into covariance. Okay, that's how I control the facility. So go. Now, look at this. This one is just like the two-way ANOVA. Okay, how do we read this? First thing we read is the facility. Okay, facility. What we control first. And here, what does it show us? Facility. Does facility affect satisfaction or not? Yes or not? How do you know? Look at the sig of facility. Here, you can see the sig is nearly 0, less than 5%. It means that facility really affects the satisfaction. Okay. Now, put it in and we control already. So, let's start just like the two-way ANOVA. Go with the interacting power first. Now, does a CD and location do they have the interacting power in affecting satisfaction? Do we? No, because the sig is 40%, larger than 5%, and this is good. Okay, so we can talk about CD and location individually. Individually, location does not affect satisfaction at all because the sig is blah 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 blah, and then the CD really affects the satisfaction because the sig is blah blah blah. It's that way. Okay. Look between the ANOVA, two-way ANOVA and the ANCOVA, you can see, what do you see? The error here in two-way ANOVA is 602, and here the error is 588. See, when you put another variable into your model, the error reduces even more. Okay. Is that good? That's good. So the more you reduce the error, the more variable you put, but cost money. Okay. The bigger your model will be. Now, anything you want to ask me about the ANCOVA here? Ask me now. Yeah, what if? Yeah, what if the sig of facility is not 0, but let's say 50%. Okay, what if it's big? It means that the control variable we put into our model does not affect the satisfaction. And what does it mean? It means that we waste money to measure it, right? But the effect of it on our DB is too small to talk about. Okay. It's normal. It's normal because we propose that nothing will happen to affect this thing, but no, it's not. It's only what we propose. No. Okay. Okay, if nothing else, then you can have a break now, and then after that, we will go further. Yeah, okay.